So today I want to talk about edge detection. There are a number of topics to be covered here, but we will not go into too much detail of each of these. I will try to give you the main idea for each concept. Uh, however, we should remember that all of these methods have been implemented in NumPy in OpenCV, and so you just need to understand the method so that you can decide what parameters to be applied when you use those functions. Okay. So with that thing in mind, we will look at all these methods. So in the previous lecture, we looked at isolated points detection using the Laplacian, right? Then we looked at the different edge models, how the first derivative and the second derivative can help us detect edge points, right? So this is what we did last time, and what I want to talk about today is some basic edge detection techniques which use gradients. Then two advanced edge detection techniques which combine the gradient methods with some other steps. So one is this Marr-Hildreth edge detector, and the other is the Canny edge detector. The Canny edge detector is the most commonly used edge detector. And then we look at some edge localization or linking edge point kind of functions using local processing and using global processing. Okay, so there are many methods. For global processing, we look at the method that uses the so-called half transform. Okay, so the typical steps in edge detection I have listed here. First, some kind of smoothing is done for noise reduction. Why is that important? So this image here illustrates why denoising is important. So suppose you have the first set of images here corresponds to an image where there is no noise. Okay, so this image and the first gradient of this image, the first derivative looks like this. Okay, and the second derivative looks like this. These are the corresponding images. Image of the is known from taking derivatives of this, and once you have these intensity values, you can scale them in order to display them as an image. Okay, so that's what is being done here. All right, so this is the original image, noiseless image. Then this is how the first and second derivatives look like. Now, if the next images, number 2, number 3, number 4, these are all images, the original image plus some noise. Okay, although if you look at the image itself, I mean, human eyes cannot really differentiate between these. If you look at this, you won't be able to say that there is noise, okay, or differentiate between the types of noise between these images. However, the intensity profile or the histogram, both of them will differentiate, and you will see that the first derivatives and second derivatives become noisy in this way. Okay, so now even if your image looked so good, just like the original, if there was some noise in it, then you can see that the first and second derivatives are giving almost no information. Okay, this kind of information cannot be read out from these images. Okay, so since by looking at the image you cannot say if there is noise or not, the best thing to do is first denoise the image, conclusions from the derivatives better. Okay. So image smoothing is what is typically usually a Gaussian blur, that is the sort of, or averaging with a box kernel, something like that. So one of these two things are the first step for noise reduction. Then detection of edge points. Okay, so detection of edge points, that is what we will see some basic edge detection techniques. And then edge localization, which means so you have found some number of candidates or some number of pixels, a set of pixels who are candidates for being an edge point. Okay, so it is, which means that you have found those pixels which are likely to be edge points. Now, out of those, which of these are exactly edge points and which of these can be discarded for some reason or the other, that process is edge localization. Okay, to decide which of the edge points that you have found in the second step are actually edge points. And finally, when after edge localization has been done, it is possible that there are gaps between the edge, the detected edge points. Okay, and you want to fill those gaps. So that is the step of linking edges. So we will look at so one we already know. We will look at 2, 3, 4. Okay. All right. So how to use image gradients to identify edge points? So it is the same idea as before. Okay, we will just look at it in some detail. Okay. Uh, and this is a very useful tool. This is the go-to step. For example, if you have some straight lines in the image that you want to detect, then it is not continuous, it is discrete. So you will have to use finite differences in order to calculate these differentials. Okay, so that's what this is. Now, this process of calculating the gradient at every point can be accomplished using some kernels. Okay, so these are exactly the kernels that will calculate the first derivative, the derivative with respect to x and the derivative with respect to y. Okay, so these two kernels accomplish this task, and I think it's quite easy to see why. So you're looking at fx plus 1y minus fxy. Okay, and remember your image is always so that x is in this direction, y is in this direction. Will be calculated using this kernel. Okay, and similarly, derivative with respect to y will be calculated using this kernel. Okay. Now, so what you can do is you can calculate this gradient at every pixel. Okay, so the effect will be again you will have, so suppose your original image is m cross n. Okay, so size of f is m cross n. Then you will have, if you take all these del f's, okay, at every pixel, then the size of del f, this will also be an array of the same size, m cross n. Okay, del f will also be an array of size m cross n. Okay, and again, like before, this del f can be scaled, the values in del f can be scaled and displayed as an image. That is the gradient image. Okay, so you can have from the gradient values, you can also have, you can just pull out the magnitudes, which means all the del f xy's, right, by calculating this. So again, you will have an array mx, these mxy values, if you put them together, it will be an array of the same size, m cross n. And you can also have these directions calculated at every point. Okay, and you can have these directions giving you an array of the same size. Okay, so each of these, the gradients itself, the magnitudes and the directions, all are arrays of the same size as that of the original image. Okay, and so we can always display these arrays as images themselves. Okay, so that is one more thing to keep in mind. So now, if we want to detect an edge point, the direction in which uh, the edge is traveling at that point. Okay, so in this way. Okay, so if you are looking at a particular point xy here, okay, the edge is traveling in this direction at this point. Okay, so the gradient at this point is going to be perpendicular to this edge direction. Okay, so that is what this is saying. Okay, alpha xy is perpendicular to the direction of the edge at xy. All right. So this is the thing to keep in mind. So now, if you want to, so as I said, you can calculate gradients using these two kernels. Okay, but it has been found that, okay, if you use just those two kernels, you are only taking into this information and this information. Okay, just these two pieces of information. But if you take into consideration more neighborhood information, you get better outputs. Okay, so instead of taking just these 2 pixels at a time, you can choose to take 4. Okay, that means you can take a 2 by 2 kernel. Usually a 2 by 2 kernel is arranged in this way around the pixel. Okay, so that the pixel itself is located at the top left corner of the kernel. Okay, so you can work with a 2 by 2 kernel, or you can work with a 3 by 3 kernel. Okay, so gradients can be calculated using one like this, these kernels, or 2 by 2 or 3 by 3 kernels. The advantage with 3 by 3 kernels is that you will take into consideration the information on all sides of this pixel. Okay, with a 2 by 2 you are looking at only one side. Okay, uh, but with a 3 by 3 you're looking at all 8 neighbors which and all sides of the pixel, so that you're taking into consideration more information. So there are so if you want to look at 2 by 2, these are called the cross gradient operators. Okay, uh, it is clear that if you use this kind of kernels more on the vertical and horizontal directions. Okay, if you want to focus more on the diagonal directions, you can use either this or this. Okay, here I've illustrated how the action of these kernels will be on this 3 by 3 piece of the original image. Okay, uh, and as I said earlier, it is even better to look at 3 by 3 size kernels. So examples of 3 by 3 kernels are these Sobel and Privet operators that we have seen before also when we looked at. That's the only difference between Privet and Sobel. There are more kernels also. These are Kirsch compass kernels, where instead of just looking at the x and y directions, you could choose to look at 8 compass directions: north, northwest, west, southwest, and so on. Okay, since our y is in this direction, so this is our north. Okay, so with these pixels being given more weight than the earlier, the other ones, and so on. Okay, so these are some more kernels. The results that you can get using these kernels can be improved by doing two things. One, you smooth prior to computing the gradients. Okay, so I have shown earlier why smoothing is important. Okay, because gradients are very sensitive to noise. And secondly, you can do thresholding. Okay, so here are some examples of size or of whatever size. Okay, and the intensity values are scaled to the range 0 to 1. Okay, and then what you see here is mod gx, that means the gradient in the x direction. What you see here are mod gy, the gradient in the y direction. Okay, and here you see mod gx plus mod gy. So actually this is the gradient image, but so earlier what I was saying, it is the magnitude. So in practice, actually, so although mxy will technically, if you look at this, it is technically square root of these. In practice, to reduce the number of computations, mxy is taken to be just mod gx plus mod gy. Okay, and sometimes this itself is called the gradient. Okay, although technically it is the magnitude of the gradient. Okay, so that's what's being done here. So they are calling this the gradient image, although what really they want to say is that this is the magnitude of the gradient. Okay, and so they have just added these two to get this. Okay, so this has been done without any denoising. Okay, and this has been done after denoising with a 5 by 5 averaging kernel. Okay, before edge detection. So what are so there are a few differences. Okay, definitely the noise that is seen in this is eliminated here. Okay, so you can see less noise in these gradient images. Okay, and you can see the details or the edges much sharper in this image than in this image. Okay, so for further processing, it is useful that this kind of noise is not there, because you don't want these pixels to uh, these intensities to come in between of your processing when you really want to look at only these intensities. Okay, so smoothing is definitely something that must be done prior to edge detection. Thresholding after computing the gradients brings out the edges even better. Okay, thresholding, like we talked about thresholding before, you choose a threshold and then just binarize the image. Okay, essentially what that does is removes all the other things that are not required and just concentrates on the important parts of the image. The important means important to whatever, with respect to whatever you are interested in. Okay, so in this case we are interested in edges, so thresholding will keep the only the edges. Okay, so you take the gradient, then you threshold. So these two so this is basic edge detection, okay, using gradients. Denoise, look at the gradient image and then threshold. So these three steps, very basic edge detection techniques, and the choice of the kernel that you use will decide what is detected better. Okay, so if you use the component in the x direction, you can see that the horizontal edges are detected better. If you use a gradient in the y direction, you'll see that the vertical edges are detected better. Okay, you can combine these two pieces of information and take by taking the sum. Okay, another way to combine is by taking the or. Okay, the just take the or operator on both these images, so that will keep these as well as these. Okay, so that is one more way of combining the information. And then you do thresholding, so that will give you the edges. Okay, so this is one basic method. There are advanced edge detection techniques because there are more these. This was a very simple image in which there were horizontal, vertical, like really strong directions to the edges. Okay, so in this case, we had really good results just by looking at gradients. But there are images where there are no such strong direction components. Okay, there could be a lot of curves, and in that case, maybe using gradients is not the way to go. Okay, then in that case, we can use some advanced techniques like the Marr-Hildreth edge detector, which is basically the LOG method that we have seen earlier. Okay, so this edge detector basically focuses on finding the zero crossings. Okay, so you remember you can form the kernel corresponding to this expression. Okay, so here is a depiction of that. So this is about the Laplacian of the Gaussian looks like. Okay, although this is in the this is the negative of it. Actually, it is going to be the other way. This is the negative of the Laplacian, because you see, for example, when x and y are 0, okay, then this is going to be a negative number. Okay, so at the origin, this is going to be negative. Yeah, so here they have said this is the 3D plot of the negative of the LOG. Okay, and the negative of the LOG displayed as an image looks like this. Okay, so this is exactly doing a blurring, but also there is a darker portion here. Okay, and this difference, because of this dark portion, you are going to see these two intensities, and that is what is going to contribute to the zero crossing. Okay, you can see this. These are what is going to contribute to your zero crossing. Okay, and that is why you want to use something like this to detect the zero crossings. Okay, this is just to detect the zero crossings. Okay, this is just a uh, 5 by 5 approximation to the kernel of the shape. Because of its shape, it's also called as the Mexican hat operator. The LOG is called as the Mexican hat operator. Okay. So, as I said, the focus of the Marr-Hildreth algorithm is to find the zero crossing. So, you filter the input image with a Gaussian kernel, compute the Laplacian of the filtered image using a Laplacian kernel. Okay. Or, yeah, so essentially, and then you find the zero crossings using the image that you get here. Okay, so after you have taken the Laplacian, then so actually I should just show you. So this is the original image. Okay, and this thing the Gaussian already applied. Okay, and then this is the steps 1 and 2, which means the Gaussian and the Laplacian being done. After that, it looks like this. Okay, so here you can see the zero crossings, right? This change in intensity. These are the zero crossings. Okay, at every edge, you will see this double line. We discussed this in some detail in the previous lecture, why this double line is seen. So for every edge, you will see a double line. That's the zero crossing. Okay, and here they have just thresholded to display those. Okay, so for every edge, you see 2. Okay, and this is another. This is one kind of thresholding. This is another kind of thresholding, which is giving a clearer picture. Okay, so you can see that these 2 lines correspond to the zero crossings for every edge. This is the Marr-Hildreth algorithm. Okay, so I should just say in the beginning that the focus is to find is on finding zero crossings. And essentially the LOG is locating those zero crossings. That's what it's doing. Okay. Then the canny edge detector. This is a bit more complicated and it involves more steps. But we will take a look at these steps so that when you, if there's a reason for you to apply the canny edge detector, you will understand what each of those parameters mean. So the canny first step, again, smooth using Gaussian filter. Next step is to compute gradient and magnitude images. That means del F and capital M. Okay, so you calculate these 2 images. Then apply non-maxima. So this step we will discuss in some detail, applying non-maxima suppression to the gradient image and applying double thresholding to finally detect the edges. Okay, so the first 2 steps are clear to you, right? So you just have to apply the Gaussian and then calculate these. So we know which kernel is being used. So there is one sort of parameter here. Okay, then the next thing to do is apply this non-maxima suppression. Non-maxima suppression, essentially, what it will do is, see, once you have this one. Yeah, let's look at the denoised one. So this is a gradient image, right? And so if we zoom in, we will see that, well, you want edges. So the best thing to have is have an edge that is 1 pixel thick. Okay, you don't want too many pixels. There should be just 1 pixel along the edge. Okay, but now here you see the edge is this entire region, right? So this edge is not just 1 pixel thick. There are many other pixels in this region. Okay, and you want to remove those. So this canny edge detector, this non-maxima suppression, is essentially the process of saying among all these, which one has the maximum intensity, maximum pixel intensity. We will keep those, and in the neighborhood of those, if there is some pixel with lower pixel intensity, we'll remove that. We'll assign a 0 there. Okay, so essentially doing this processing at every pixel. You pick up a pixel, look at its neighborhood, okay, see which one is the one which has maximum pixel intensity. You keep that and remove all the others. So do this pixel to pixel. Okay, so you keep on doing this for all these detected candidates of edge pixels. That is the idea of non-maxima suppression. Okay, so you will have kept some and removed some. Okay, now what will happen is, even after doing that, it is still possible that you will have pixels because they were, you know, sort of maximum in their own neighborhood. Okay, so you might still have pixels that are not true edge pixels. So this non-maxima suppression doesn't solve the entire problem. Okay, although it reduces the set of pixels to look at. Okay, so in that case, so after that, canny edge detection, there's another step of thresholding, where one more filtration of these pixels is done. Okay, so one more time you look at the pixels with maximum intensity and remove those with lower intensities. Okay, now see, this process would have been very simple if all these pixels had the same intensity. Then you would just say, you just keep the pixels with intensity 1 and you're done. Okay, or pixels with whatever this intensity, if it was uniform throughout, there would be no reason for doing all this. But that's the problem, that now if you just do, okay, if you think you might just threshold by keeping all the ones and removing everything below 1, okay, then you will see that there are lots of gaps, okay, because not all these pixels along the edges have intensity 1 or intensity 255, if you like. Okay, and so that process of thresholding right here will not work. You will get gaps, and that's exactly what you see in this. Okay, they have thresholded the gradient, but now you see there are gaps here. Okay, there are gaps here, all these gaps. Okay, not only that, the edges are not 1 pixel thick. Okay, so this is not just one thin line along the edge, but this is a number of pixels along the edge. Okay, so both these problems are dealt with in the canny edge detector. You want to reduce the gaps, and you also want to have 1 pixel thick edges. Okay, so oops, yeah, so coming back here. So this process of non-maxima suppression, as I said, what one does is you look at the gradient image, okay, and then you look at certain directions in which processing can be done. I thought I have, yeah. So suppose you are looking at the pixel at the center here. Okay, so this is a piece of the image, and you're focusing on this pixel. Okay, and there's an edge here. That means this pixel is lying on the edge. Okay, so this part is darker pixels, these part are lighter pixels, so there's an edge. Okay, and then in that case, the edge normal will have either this direction, or if it is, this situation is reversed, then the edge normal will have this direction. So what non-maxima suppression will do is, first of all, you divide this neighborhood into some regions, some angular regions. Okay, so like this. Okay, and 4 pixels, then these 4 pixels, then these 4, and these 4. If you have divided it like this. Okay, so you focus on those directions one at a time. Okay, so here it is. Yeah, so you look at a 3 by 3 neighborhood. For this neighborhood, in the gradient magnitude image, which means in this norm of del fxy, you have this image, right? So this image is telling you the magnitudes of the gradients at each pixel, and this is telling you the directions of those gradients at each of the pixels. So we have these two images, and we are going to go along these two when we work. So for this neighborhood in the gradient magnitude image, find the direction closest to alpha xy. So you have, so let me do it this way. This is the pixel of interest. This is the magnitude image. Again, same pixel of interest, but this is the direction of the gradients. Okay. Now, in this matrix of directions, you find among these 8 neighbors, you find which pixel has direction closest to this one. Okay. So suppose it turns out that this pixel here has direction closest to this one. So how is this closest being measured? With just so these are numbers, right? So just distance now. Okay. So or absolute values. So you look at this one. Okay, so suppose this is closest in magnitude to this alpha. Okay, then this pixel you look at here. Okay, and then you compare the magnitudes at this point and this point. Okay, now the magnitude here we know is k. Okay, that is what this k denotes the magnitude here. Okay, and suppose the magnitude here k is less than this one, then what we'll do is we'll remove this pixel and keep this pixel in our set. On the other hand, if this magnitude is greater than this one, then we'll remove this one and keep the k. Okay, so essentially what is happening is you have so many pixels in your image, and these are all your candidates for edges. You are going to remove few of those by this kind of comparison. Okay, you see which of them are closest in direction, and then you compare the magnitudes and you remove those which have lesser magnitudes. So in this way, we will reduce the number of pixels that are candidates for edge pixels. This is called non-maxima suppression, for obvious reason that you are removing the pixels whose magnitudes are, or the magnitude of the gradient of those pixels is less. Okay, so in this way we are removing some pixels. That is this process essentially. Okay, then thresholding. This threshold. So now we have removed some pixels and we have reduced the number of candidates for edge pixels. Now among those also, we can have some spurious or not correct edge pixels. So to remove that, we will do thresholding. This term hysteresis essentially is double thresholding. Okay, so we are going to use two thresholds and some processing in order to do this. So there is a low threshold TL and there's a high threshold TH. Okay, so this low thresholding, suppose you have your original image. So this is your original, just piece. Okay, this is a piece of the original image. After you do thresholding, then you are going to have some. So this is your original image F. Okay, with the low threshold, the image we are going to call it GNL. This is your GNL. Thresholded F with the lower threshold. This is thresholded F with the upper threshold. So this is GNH using the upper threshold. Now clearly, if TL is less than TH, then the image or the pixels that are in GNH are going to be contained in GNL also. Right? So GNH is actually going to be, if you look at it as a set, then this is going to be a subset of GNL. Okay, the pixels here are going to be repeated here. Right? So we take the difference. Yes, should be there somewhere. Here. Okay, so we take the difference from GNL, we remove GNH. Okay, and so what is going to happen now is that this GNL, if you look on the intensity scale, okay, so on the intensity scale of 0 to 255, you had a low threshold L, then you had a upper threshold H. Okay, and GL earlier was all pixels lying in this threshold or this range. Okay, and GNH was all pixels lying in this range. Now what we are going to do in this step is subtract. Okay, so it is going to be all pixels that lie only in this range. So these are now disjoint sets. Okay, so GNH now is the set of pixels lying in GNL is pixels lying in this range. GNH is pixels lying in the other range. Okay, so now what we have done is we have broken up the image into these two categories of pixels. Okay, and so what we are going to do now is, first of all, we realize that these are very strong candidates for edge pixels because their intensities are really high. Okay, so these are the strong pixels and these are the weak pixels. And now what we want to do is we want to decide based on the intensities which weak pixels we should keep and which we should remove. Okay, so for that what we'll do is we'll look at every pixel in these among these strong pixels, look at the neighborhood. Okay, if we find a pixel in here which is connected to this P, okay, then we keep that pixel. And so essentially what I mean, so suppose you have a strong pixel P here, okay, and which means in GNH. And now suppose here you find a pixel which is not in GNH, but it is in GNL. This pixel is in GNL. Then you will keep this pixel. Okay. So in the 8 neighborhood of P, any GNL pixel that will be kept. But if there is a pixel here, say away from the 8 neighborhood, which is in GNL, that will be removed. So to put it in one line, all those pixels in GNL which are not in any 8 neighborhood of pixels of GNH will be set to 0. Okay, and only those which are in some 8 neighborhood of P in GNH will be kept. Okay, so this way we reduce some more. Okay, so these all we will keep, and from these we will keep only those that are in some 8 neighborhood of pixels in here. Okay, and this way we reduce the candidates even more. All right. So this is also going to lead to filling the gaps. So there will be a lot of gaps in here. But now since you are going pixel to pixel and looking at connected pixels, so this will also lead to linking. Okay, the gaps will be filled in this way, and we will have just 1 pixel thick edges. Okay, so here is the example. So example that we were looking at before also, same image. This is obtained using the gradient and thresholding. Okay, so this was the image that we saw before, which had these gaps. Okay, this is the one with Mar-Hildreth, where we have detected all 0 crossings. Okay, and this is the one with canny edge detection. Okay, so we can see that so some of those gaps are filled, but some are not. Okay, so some gaps are still remaining. But see here, because the direction is a strong thing, one would prefer to go with the gradient image. Okay, even though this is not 1 pixel thick. If you want 1 pixel thick, you can go this way. Although the strength of this depends on the thresholding that is chosen. Okay, so you have to choose this L and H. Okay, so the lower threshold and upper threshold. Depending on the choice of this, you will see the strength of these edges. Okay, but the better illustration of the canny edge detector. Okay, so this image does not do justice to the canny edge detector. Let's look at this one. Okay, where there are no strong directions. Okay, so this is the original image. This is the one with gradient and thresholding. Okay, and then you can see there is noise. There is the edges are not thin. Okay, and there is just too much information here. Okay, this is the effect of the Mar-Hildreth method. So again, you can see a lot of noise. Okay, although this is much better than the gradient. Okay, this has sharper edges. Okay, and this is the effect of the canny edge operator. Okay, and then you look at the original and look at the edge detection by canny. Okay, and possibly this is what you would want to see if you did. So even these small objects or small artifacts there, the edges are being detected quite well. Okay, see this kind of noise you cannot avoid. Okay? This noise we cannot avoid, but this is still doing a much better job than the gradient in this case. So here also you can see, and the thickness of the edges is, these are just 1 pixel thick. Okay, so for example, if you had to do further computation, like calculating the length, uh, or calculate doing some calculations from this or measurements from this, you would prefer this to something like this, because here you wouldn't know which pixel to trust, or I mean which pixel to choose for your measurement. There are many pixels here, then you would have to make a choice. Here there is no such question. Okay, you just look at that pixel which is white, okay, whose intensity is 255, and measure using that. Okay, so having one pixel thick edges is extremely useful in for further computations. Uh, okay, so this was the canny edge detector, and finally, I want to talk about linking the edges. So so in this image, if you wanted to link these, okay. Also, linking is much easier in canny than other, because again, because the edges are 1 pixel thick. Okay, there aren't too many spurious pixels here, so linking is easier after canny edge detection. So there are some local processing methods. One we already saw linking edges was this hysteresis or double thresholding. Okay, if that doesn't suffice, you can do more. So one of the local processing methods is to use the magnitude and direction of gradient vector again. Okay, so simply you just look at the magnitude image and the uh, directions image. Okay, by using a thresholding on the magnitudes and some by restricting the directions. Okay, so what happens by restricting the directions? You're looking at all pixels that uh, that are sort of pointing towards the same direction. Okay, so that is what this means. So you fix an A, this is a fixed direction, okay, plus minus a certain epsilon, okay, and so here plus and a certain acceptable angle deviation, and you look at only those. Okay, so for those you keep gxy is 1 and 0 otherwise. So this is sort of a binarization being done based on magnitude, acceptable magnitudes, as well as acceptable directions. So we break up the image using these two conditions. This is an AND, so both these conditions have to be satisfied. Once you have discarded all other pixels and just focused on these two conditions, then you simply fill the gaps of zeros, okay, of certain specified length, because the directions, they are going to be all in certain directions only, right? So you will find these gaps of zeros which you can fill with ones and join the edges. Okay, so this is you can do this in a fixed direction, then you can change these rotate by something being done in these two images. That is the intermediate image they didn't show. And a very popular way is using the Huff transform. Although the idea of Huff transform is entirely different from all the ideas that we have seen till now. So everything else till now was based on gradient, magnitude, direction of the pixel values. But the Huff transform is an entirely different idea, where Huff's idea was you just change the parameter space, and then you will get some more information about collinearity of the edge pixels. Okay, so this can be done not just to find collinear points, but can be done using other parameter spaces. This can also be used to detect circles. Okay, so there are Huff transforms for circle detection, but we look at the Huff transform for line detection. Okay, so we will just look at the parameter space in which lines are detected. You can this can also be adapted to other shapes. Okay, so this processing using the Huff transform is useful when the edge map is available. Edge map means something like this, okay, or the thresholding of this one. Okay, so that's an edge map. When the edge map is available, then you can do. So edge map you can get by doing any of the earlier processes, right? So the point of half transform is to connect the. So if you do canny, let's say first, okay, this can be your base for applying the half transform, and the half transform is going to hopefully join all these. Okay, so you start with an edge map, and then the approach is based on identifying whether the specified pixels lie on curves of a specified shape. The specified shape for us is a line. So we want to identify whether two edge pixels are collinear or not. Okay, so that is what we are going to focus on. So there is one very naive idea that, see, if you have n points in an image, then and you want to find all subsets of points that lie on straight lines, then essentially you can, I mean, very naive way of thinking is you can find all lines that are determined by every pair of points. Okay, and how many are these? These are n times n minus 1 by 2. If you have n points, n edge pixels, then you can find all the lines. Okay, plot all the lines that are determined by these points, and you can check for each point line pair, you can check whether the given pixel actually lies on that line or not. Correct? For every point line pair, you can do this check. But see, the number of computations required for doing this process is too many. Okay, because you will have not 10 or 20, but you can have thousands of pixels that you want to check. Then just look at the number of lines and line point pairs that you might need to check. So this is a very expensive way of doing it. Okay? So Huff's idea was to change the parameter space and look at this problem. So the general parameter space change idea works in the following way. So here the image is in the x is here, y is here. Okay, so this is the image in the xy plane, and suppose we have 2 points that are collinear. Okay, that means both of these points lie on a line. Let's call it y equal to ax plus b. Okay, so suppose these 2 points lie on the line y equal to ax plus b. Then instead of looking at the parameters x and y, we look at parameters a and b. Okay, so look at these 2 points, not in the xy plane, but in the AB plane. Now, what is going to happen in the AB plane is that if you have a line here, okay, since all the points on this line correspond to the same pair AB, okay, the line is going to correspond to a point in the AB space. Okay, so every line corresponds to a point here. Okay, and every point, since there are many lines that can pass through this point, right? So every point here will actually correspond to a line here. So you can think of it like this. So if your line was y equal to ax plus b, okay, then you can write it as the line b equal to ax1 plus y1 here. Okay, so where is that? So they have used a different notation. That's okay. So the point x1, y1 on L corresponds to this line in the AB space. Another point x2, y2 on L will correspond to another line in the AB space. Right? Because now your parameters are A and B. And these 2 points, if they were collinear here, then the corresponding lines will intersect here. And that is the key point. Okay. The important point for us is that in the parameter space, if you're looking for collinear points, then collinear points will give rise to curves that will intersect in the parameter space. Okay, and so this is the thing to note. If you're looking for points on a circle, okay, if you want to detect circles, Then you want to make your parameter space such that any 2 points on the same circle will give rise to curves that will intersect in the parameter space, because essentially it is this these intersections that are going to make the Hough transform work. Okay, so we are going to count how many or which points give rise to intersecting curves here. Okay, and those points will be collinear. We'll say those points are collinear. Similarly, for circle, you will want to see which points give rise to intersecting curves. Those points lie on the same circle, is what the conclusion will be. Okay, so this is the idea of Hough's transform. Okay, in the case of lines, okay, if you want to detect collinear points, that means you want to detect lines in the image. Then we use the R theta parameterization. What is the R theta parameterization? It's the normal form of a line. Okay, so here is the X and Y. This is your image. Okay, and there's a line in the image. Well, every line can be expressed uniquely using the perpendicular distance of the line from the origin and the angle that this vector makes with the x-axis. Okay, so using this R and theta, you can determine the line. So this line corresponds to a point r comma theta in the r theta space. Now, if 2 and any point will give rise to a curve in this space, right? A fixed xi, yi will give rise to a curve in this r theta space. And so if two lines here are, 2 points here are collinear, they will give rise to intersecting curves in the parameter space. And that's what we will do. The steps of the Hough's transform do the following thing. They break up this theta into some number of bins. Okay, so the range of theta in some number of bins. The range of r is broken up into some number of bins. Okay, and you sort of make these cells. Okay, so these are called accumulator cells. Accumulator cells because they will accumulate intersection values. How? So for every, so suppose you fix this. Okay, so this is some ri theta j. Okay, what you do is you try to see if this ri theta, if some number of curves are intersecting at this ri theta j. Okay, so this point is corresponding to this one. Say if you see some number of lines intersecting at this, some number of curves intersecting at this point. Okay, then it means that the original points corresponding to those curves were collinear here. Okay, so in this way, for each of these cells, you give a score to each of those cells depending on how many curves are intersecting at those points. Okay, so some cells may have a score 0. That means that no two curves are intersecting there, which means you couldn't find any line corresponding to that cell. Okay, but some cells might have high number of values. So suppose you have a high number k here, then that means that there were k curves intersecting at that point, which means there were k points here that were collinear. So all of those you can just join by a straight line. Okay, so that is the idea of Hough's transform. Okay, and so the way the algorithm goes is that so what you do is your theta is going to range from theta min to theta max, right? For every value of theta, you calculate a corresponding r. So you let theta vary, calculate the corresponding r. Okay, whenever this number comes out to be greater than 0, you just mark it here. So I have written out the details here. Yeah, so you would decide bins and decide bins for r and j. Okay, for every edge point xy, so you have the edge map. So you have candidates for edge points. You pick up any edge point xy, use that xy, and for every theta I between theta min and theta max, you calculate these r's. Okay, so you will get values. For theta min, there is something for theta 1 there is some r, theta 2 there is some r, and so on. Correct? So you will get these pairs. Then you assign 1 to each of the accumulator cells that correspond to these pairs. Okay, so every time you get a pair, you will get some value of r, right? Corresponding to every theta, you will get some r. So which means you will get these pairs. For each these pairs, you assign a 1 in the accumulator cell, wherever they may be, wherever this ri theta j occurs. Okay, so in this way, the cells get a vote. So basically, a cell gets one vote for each edge point that's found to be collinear with the first edge point corresponding to that cell. Okay, so if there is already a 1 here, and you find another edge point that's collinear, you will get another vote here. Okay, and this way the votes accumulate. If a cell has k votes, this means that there are k points which are collinear, which correspond to the cell. Okay, so now finally examine the counts of the accumulator cell for high pixel concentrations and fill the gaps by examining the edge point distances. So you look at accumulator cells for high pixel concentrations, wherever there is the number of votes is high. Okay, then you infer that those were the corresponding points that were collinear, and then you join them. So joining also, this examining edge point distances means you join with respect to a certain threshold. You say if these points are this far from each other, then you join, depending on your situation, okay? Depending on the kind of work that you're doing. So here is an example. So here is an image with 1, 2, 3, 4, 5 dots. Okay, 5 white pixels are there, and you want to find the collinear points in this image. Now, if one applies the half transform to this image, okay, then in the r theta space, corresponding to every point, corresponding to 1, 2, you will get these curves. Okay, so they have just numbered those points in order to be able to recognize. So 1, which is here, which is the origin here, okay, will correspond to this horizontal line. Okay, 2 corresponds to this curve, 3 corresponds to this curve. This is 4, and this is 5 here. Okay, so there are these 5 points corresponding to 5 curves in this, and these 3 curves are intersecting. The curves corresponding to point 2, point 3, and point 4 are intersecting, which means these 3 curves correspond to points that were collinear in the earlier image, and that is the case 2, 3, 4. There is also 1, 3, 5. These points are also collinear. So let's see if 1, 3, 5 intersect. So 1, 3, and 5 intersect here. Okay. So this point will have a higher value in the accumulator cell. Correct. This point will have a higher. So this will have 3 in the accumulator cell. This point will also have 3 in the accumulator cell. On the other hand, this will have just 2 in the accumulator cell. Of course, this point is telling us that this intersection is telling us that the corresponding points were collinear in the original image, but these are just 2. So of course we will, since any 2 points are collinear, these kind of intersections will have to be ignored. Okay, we look at only higher scores. Okay, and so this 2 tell us that these sets of points are collinear. So that's essentially the half transform for lines. Similarly, half transform for circles can also be designed. Here is an example. Okay, so here I think they have applied canny. Yeah. So this is the image of an airport, satellite image of an airport, and they want to determine the straight lines in this. Okay, so the canny edge detection is applied, and an image like this is obtained. Okay, but however, in real life, this is one straight line. Correct. So you want to detect this entire thing so you don't want these gaps. Okay? You want to detect this thing as one straight edge. Okay, and so one can apply the half transform. Okay, and so half transform, which it's been localized to these edge pixels. Okay, so it's being worked on only these edge pixels for now. Then it will recognize that these points are collinear. Okay, and then if you just add that to the original image, then it's saying that this entire thing lies on one line in the image, okay, which is the case here. Okay, so this is just for illustration purposes. Okay, in practice, it will, I mean, the original image also, it might not be so clear. Okay? Another thing is that sometimes in the original image it is clear, but when you do processing, when you do thresholding, that information is lost. Okay, so you want to bring back that information also. That is also one way or one reason why you may need to link the edges. Okay, so that's all for now. So next time we will look at segmentation. So I will try to cover all segmentation methods.